Happy to announce our next speaker, who is Mohammad Rastegari, who is the CTO of his own startup, Xnor.ai. He's looking at ways of doing CNN models that take fewer resources, fewer memory, presumably less power. All good things. I'm sure there's got to be a but there somewhere, so hopefully we'll hear the but coming up. So, thanks. Let's welcome Mohammad. Thank you.
Thank you, everyone. Thank you for having me. I haven't tried the clicker. I hope that it works. So today I'm going to talk about efficient structure of a convolutional neural network. In a sense, how we can build efficient convolutional neural networks. These are mainly categorized in two categories: model design optimization and training optimization. There are a bunch of approaches on model design optimization. We'll touch on that, and there are a few approaches on training optimization, which I'll discuss about that. So these days, behind any AI task, there is a very deep neural network. And convolutional neural networks are one of the most common choices for computer vision applications. And then the key operation in this type of networks are a convolutional operation between two real-value tensors. And then the elements of these operations are simple arithmetics that the problem is that there are billions of these arithmetic, like multiplication, summation, and subtractions, that makes it very difficult. And that's why we need GPU to parallelize this operation to make them faster. So the first approach to build a more efficient convolutional neural network exploits from the fact that the tensor types between these convolutional operations are real-value tensor, which normally represent with 32 bits. We can reduce the precisions of these data structures to save in memory and computation. But what if we take this to its extreme scenario when we reduce the precision to a single bit? In this case, we represent this with -1 and +1. If we do that, then all the arithmetic operations can be converted to logical operations. For example, the multiplication can be converted to Xnor operations, and all the addition and subtraction become a simple bit count known as pop count in the hardware. So why binary is good? For obvious reason, because these binary logical gates are natively already implemented in most of the commodity CPUs that we are using these days in our phones, in our many other devices. And then they can be parallelized inside CPUs. And then they can be used for very low power devices that we are working every day. And the other good benefit of them is that they're very cheap to be implemented inside the hardware for designing a new type of neural network chips as well. So now, let's see what are the different possibilities of building a neural network using logical operations or binary operations. First, as that I mentioned, the convolution is usually between an input tensor and a weight or parameter tensor in a network. So if we just binarize the parameter, it means that we don't need to do any multiplication operation. All we need is addition and subtraction. In that sense, we can reduce computation by a factor of 2, but memory we can reduce by a factor of almost 32. In theory. And then if we binarize both the input and the weight, it means that the entire convolution can be done with logical operation. In that case, the computation also can be reduced by a huge factor, depends on the register size. So let's see how we can build a binary convolutional neural network. So the convolutional operation is simply taking the filter and then element-wise product with all the spatial location inside the input tensor. And then this means that if we look at one chunk of this element-wise product, we have product between two real-value tensor, which we want to approximate this with a product of real value and a binary tensor. In fact, we want to approximate a real-value tensor with a binary tensor. And that has a very simple solution, which we can simply take the sign of the values inside that tensor. But the problem is that if you do that, you're enforcing a huge quantization error that basically destroys information. To compensate for this quantization error, we introduce a scaling factor to that estimation or approximation that we want to actually jointly minimize to finding this scalar factor with the binary values of the tensor at the same time. Luckily, there is an optimal solution for this joint optimization that we can use in our models. And with a little bit of more math, which I'm not going into that, we can expand the same thing to estimating the binary value both for the input and the weight value as well. So if we do that, then we are converting a convolution between two real value tensors into a convolution between two binary tensors. That we can save a lot of computation. But the main problem is that how should we train a neural network that it can adapt the binary values? Because the standard way of training neural network uses the gradient descent or backpropagation algorithm, which heavily relies on continuous values. And a naive solution to that would be simply training a neural network based on the like real values, and after training is done, we just simply binarize with our quantization method. And if we do that, we basically destroy all the information in the network. What I'm showing here is the accuracy of a full precision model trained on a residual net with 50 layers on ImageNet classification, which is a data set containing 1,000 classes. And you can see that the full precision can reach to a 75 close accuracy on top one classification. But if you do this technique, it almost destroys all the information. You will get close to random. And in fact, we are looking for a set of real value parameters that if we binarize them, then we can reliably predict the content inside the image. And in order to do that, we had to modify the learning algorithms of a convolutional neural network. We basically built a new type of backpropagation algorithm that can find a binary values, or that can find a set of real values that if we binarize them, they can minimize the loss functions. And the trick here is that during the optimization, we always keep recording the real values, but during the forward pass, we pass with the binary quantized one, and then we calculate gradient with respect of the binary values. But when we want to update the parameters, we update the real value parameters. In this way, we will find a set of real value that if binarized, they are suitable for our end task, which in this case is classification. So then if we do this way, you can see that if we only binarize the weight values, we almost get on par accuracy with the full precision, but when we binarize both input and the weight value, still accuracy is good enough, much better than the random, but we see a gap here. We can improve this further. I will discuss later how do we do that, but for now, let's stay with that this gap can be filled with some method later. So next approach to build a efficient convolutional neural network model exploits from the fact that all these convolutional neural networks are usually over-parameterized, meaning that there are so many redundant parameters in a single convolutional neural network. So let's look at one of those parameters, which is known as a weight filters. These are assuming that is a 3x3 weight filters. If you look at the one chunk of vector inside this filter, and if we believe that there is a lot of over-parameterization and there's a lot of redundant information, there has to be a set of these vectors that we can call them as a dictionary vector, that any other vector can be reconstructed by a linear combination of few of them. So then, in this case, any vector in a filter can be reconstructed with this dictionary with a few number of them. So then we actually don't need to save these filters into the memory. All we need is to keep a bunch of indices of the dictionary and their linear coefficient to reconstruct those filters. So the problem is that now we want to, instead of convolving the actual 3x3 filters with the input tensor, we want to use those indices and dictionaries to do the convolution. How do we do that? It's actually very simple. First, we simply convolve our dictionary elements with the input tensor, which are usually a 1x1 tensors, which is very simple to do the convolution. And then we simply use our index. For each filter, we look at the indices value and the coefficient, and based on the indices, we just look up the channels that indices are pointing to, and then we linearly combine those channels. If we do this, then we can exactly get the same result as the convolution. So, and then this produces our output channels. So then the problem is that how to train these discrete index values. Again, the index values are discrete values. There is no real mechanism for training. Again, backpropagation highly relies on continuous values. But let's see how we can do that. Luckily, there is an equivalent version of this whole process of lookup and adding with a sparse matrix convolution. If in this case, I'm looking at this matrix P, each non-zero values, in each non-zero channels actually corresponds to the indices of our index tensors, and the non-zero values corresponds to the coefficient values. Basically, if I convolve these sparse tensors with this tensor S, the output channels is exactly the same as the process I just showed you previously. So now this makes our life much easier during training, that now we can convolve the input tensor with the dictionary first, and then there is another convolution with a constraint, which is a sparsity constraint that we enforce it usually with some regularization term, for example, like L1 norm regularization here that can forces a sparsity to our tensors. And this becomes an end-to-end standard neural network training, but during the inference time, we do all those lookup to make it faster. So if we do that, of course, as we increase the sparsity, we get more speed up, but the accuracy decreases. And the other benefit of this type of approaches is that because we have a fixed set of dictionary element, we can share this dictionary among different layers and among different networks, and we can simply train the other elements of the model, for example, the coefficients, and that makes the model much more generalizable, and then it enables us to train with very few examples. Those other plots, I'm showing that the models that we can train with only seeing one example per categories. And then also these models are very fast to train, meaning that with very few iteration, we can get higher accuracy. And these line of works are very suitable when you want to train a model on the device, that you don't want to show so many examples and you don't want to spend time on training on the device. So this type of approach is actually helpful for those type of models. Another approach to build efficient convolutional neural networks are based on actually designing a structure for a convolutional neural network to be efficient. So the standard structure of convolutional neural network follows this path that started with high resolutions, and then during the layers, it reduces the resolution and process for the high-level information with more channel and lower resolution. But this doesn't have to be like this. For example, some images contains very small objects in them that demands for higher resolution, that they want to go through higher resolution all the way into the network. And some other images, they don't have much of like a small object. They don't really need high resolution all the way through the network. And some images, actually, they don't have any small objects. They are very simple images that they all can be processed with low resolution path. So if we just put a decision at each layer, and we learn this decision function that a network at each layer can decide which resolution path wants to go, in this way, per sample, we can be more efficient for simple images. So with this simple approach, we could also reduce, not only reduce the speed of not only we could increase the speed of the model, but also we could increase the accuracy of the model, and in fact, we could beat a state-of-the-art neural network in this case with much less number of floating point operations here. And then that shows that most of the gain came from predicting small objects in the images. We've seen a lot of gain of predicting, doing a good job at detecting small objects. So if we want to have more efficient, we need to dig more into the convolutional operations. So as I mentioned earlier, the convolution is a simply element-wise product between the elements of a weight filters and all the spatial location of a tensor. So this produces a single output channel for us. But we can do the same operation by grouping each convolution into multiple groups, and then when we are convolving, we do each group separately. In this way, we can produce more channels with the same number of operations. If we take this approach up to its extreme, which the number of groups is equivalent to the number of channels, then we call it like a depth-wise convolution, and it's very efficient. But the problem is that usually these guys are not very accurate. I'll discuss later. And another way of looking at convolution, if we look at it from the spatial domain, the other side of the convolution, we have a filter that we convolve with an input matrix. And so if we want to capture larger receptive field in the standard convolutional neural network, we have to have multiple layers of these guys. But what we can do, we can spread out the elements of the filters and build a dilated convolution. And with different dilation rate, we can capture higher receptive field from the input. So when we combine the depth-wise and dilated, we reach out to a very efficient operations that we call it depth-wise dilated convolutions. So if we replace the standard convolutions with this depth-wise dilated convolution in a network structure that we usually work these days, we see some artifacts. This is a task of detecting object boundaries for image segmentation. You can see that there are some greeting artifacts using this, and these are mainly because of those holes in the dilated convolutions. So it means that we need to do something with the structure of the network. The naive structure could not work here. So we devised another architecture that we hierarchically combines this dilated convolution in different ways, ensuring the same number of operations. And if we do that, then we can get rid of all those greeting effect and artifact in the convolution. So in fact, building an efficient structure building a structure is important to gain accuracy using efficient models. So that showed a huge improvement on image segmentation that compared with one of the state-of-the-art methods for image segmentation. With almost half of the number of operations, we could get very close to the accuracy of the state-of-the-art with this model. So we still can go deeper into the convolutional operation, see how it can be more efficient. So a single convolution, the capacity of single convolution is very important. Right now, we are not using the complete capacity of a convolution. If you look at the current convolutional method, if you look at, if I just color code the channels, if I reorder the channels, I still can produce the same output, meaning that there is a reordering of the weight parameters can produce the same channel. And that's important because it means that we are not encoding any information into the order of the channels. So that's why we need to spend another layer after depth-wise convolution to fuse these channels. This is usually done by a one-by-one convolution to fuse the channels, and that's known to be expensive. So what we do here is that instead of doing single-dimension depth-wise convolution, we propose a dimension-wise. We basically do the depth-wise across different dimensions. In this way, we ensure that all the channels, also the order of channels, gets into the account when we are performing a convolution. Then we don't need to do that expensive channel fusion. Now it can be reproduced with a very fast channel fusion where we only pull a vector from the output tensor and we fuse that vector and then propagate into the next tensor. That saves a lot of computation for this task. So that shows that under the same number of flops, we can reach higher accuracy in task of image classification, and shows that the number of operations in different type of image size reduces by large margin. So if I want to summarize all these techniques, you can see that this is a golden curve that we all should care about. I always tell my team that this is the one that you should sleep with. And this means that the upper left of this curve is very important. If we push points into the upper left, it means that it's a good trade-off between accuracy and speed here. So far, like the dimension-wise convolutions are the one that is reaching to that point better. So this is the curve that every day we are trying to optimize and summarize all the method here. So now that we have talked about all the model design optimization, we care about the accuracy. I just mentioned accuracy also important. These models are usually, we are crippling these models to make them more efficient, but we care for them to be more accurate. So there has to be other training optimization for this model to be more accurate. So let's discuss about the training. In order to understand that, we need to know about the elements of a supervised learning model. The three elements are data, model, and labels. Data has been studied a lot. We have like large-scale data sets like ImageNet, and we have a lot of data augmentation techniques that already exist. And then models also have been studied for many years. A statistical model like support vector machines, deep neural network itself, optimization techniques, stochastic gradients, and all those have been studied a lot. But labels is a key element to supervised learning. We always accept learning as it is, and then as we never thought about what we can do with the label. So let's look at this image. This is one image from a ImageNet class. It's Persian cat. But clearly you can see there is an object in that image called, which is ball, which is another category of ImageNet, which is not labeled in this image. So in this sense, the labeling here is incomplete. And then look at this image. One of the common practice in data augmentation is random cropping. to prevent overfit, to prevent overfitting and have a more generalized model, people usually do some random crop out of the image and then pass them to the training with the same label. And these random crops could be very small. If you look at these two crops, you can't barely say that if they are from different categories of object. They are very similar, but the network has to distinguish these two. But if you look at the full images that they came from, they're completely different categories. So in that sense, labelings are very inconsistent. And then the other problem is that the labels are kind of taxonomy dependent, meaning that if I have an image of a breed of dog, if I predict a different breed of dog rather than I predict a completely different category of object, they will receive the same penalization. So, but for me, it's okay if I can predict it as another breed of the dog. I should not receive the same penalization for that. So the ideal label for us should have these properties. It should be soft, meaning that it can capture all the categories of objects inside the image. It has to be informative, meaning that if there is an object that has some similarity with other objects, for example, a dog which is similar to bear, it should capture that as well. And it has to be dynamic, meaning that for different crop, for different part of image, it should produce different labels. But how should we build that? This is very difficult. This is not something that you can hand out to Amazon Mechanical Turk to do this labeling for you. So in order to do that, we built a new model, a new approach for that. So this is what I'm showing here is a model that I trained with AlexNet, for example, on ImageNet. And then this curve shows train accuracy versus test accuracy. And then perfect generalization happens when test accuracy and train accuracy are the same. That's on the diagonal line. So right now, each point shows the accuracy of each class. There's 1,000 points in this curve. You can see that that curve is very far from the perfect generalization. So I just trained this model, and I reached to accuracy of 57.93. This is like a standard AlexNet accuracy. If I use the output of this AlexNet model, this network, and then start using this output, probability output, as a new label for training another model from scratch, then I can see that that curve is moving toward perfect generalization. So these probabilities, if you look at them, they have all those things that we need. These probabilities are soft, they are informative, and they will change with different crops. If I repeat this task, meaning that again I pick the probability of this new network as a label for the previous one and retrain from scratch, I will get to the point that actually my accuracy improved a lot, and I'm getting very close to the perfect generalization. And this is the one that if we actually apply this onto all those models, it improves the accuracy a lot. And there is this beautiful paradox in this. If these networks were so perfect that at each step they could predict the output exactly, then we couldn't see any of those improvements. The reason that they're improving is because those networks are not strong. They cannot predict exactly the same output. And that's perfect for efficient design of neural network. When we are actually crippling the neural network, now with this method, we can fill the generalization gap of this model and build a more efficient. For example, on AlexNet, you see that these are the models for many years. People thought that they are saturated, and then all the improvement was close to or below 1%. And then it gets to 10% improvement on this case. So to summarize all these methods, I want to show you how far we can go. How far we can go with all those efficient techniques. We have discussed about all type of building and optimization, model design, training design, but are they getting in practice to somewhere or not? So 2 years ago, when we showed a model running on a cell phone, we were so excited. We showed that with this efficient technique, we built model that can run on very low power CPUs rather than very beefy, extensive GPUs. And then that opens a lot of possibilities people were using on that. And then later, 1 year ago, here in this conference, I demoed this Raspberry Pi Zero device. And I showed that actually with this type of efficient model, we can run deep neural network on a $5 compute platform, Raspberry Pi Zero. And this to us was very phenomenal that these are like a self-battery powered, very cheap, can be bought. Sometimes I I call them disposable AI because you could just throw them away. This entire box can cost you less than $10 or like less than $20. So, but today, for this year, we have even something better here. So with all of these techniques, we were enabled to actually deploy those heavy deep learning model on type of hardware that we custom built that they are so low power and so efficient that can run with solar power, meaning that now they don't need to be charged and they are super cheap if they produce in scale. They could be sub-dollar price, yet running all those difficult deep learning models that used to be run NVIDIA GPUs on a solar power. It means that they can be massively scaled. So being solar powered is just a showcase that how efficient this could be. Another way to put them in the power efficiency, if you attach a coin cell battery to them, they can run for many years until the battery life is basically done and finished. So this opens a completely new type of possibilities for AI, the new type of applications that before we couldn't do. So efficiency matters a lot, and these were all the type of models that we designed to get to this level of efficiency. By that, I basically conclude my talk.
Any questions? Please head to the microphones if you do.
So for the refinery models, don't you ever have to worry about drift and seeding in more mistakes? That if you have a mistake in the original label, that's 5%, it'll just grow in magnitude as a possibility? Or what would you do to try and minimize that effort? So incestuous models and labeling.
That's a great question. So actually, the drift would not happen because we are training from scratch. So let's say that if you are predicting some of the labels like as a completely wrong objects, yes, you will classify it as a wrong object. But the amount of new information that you're collectively getting from the data set is much, much higher than those misclassification. So that's what we show, and I show that we always get improvement in accuracy with that. So because you can imagine an image of like the sky with a building, and then the category of this one is a building. And then during the training, you have a crop which there is no building, it's in the sky in that. And then you want this picture to be categorized as a building, which is impossible. There is no building in that. Whereas when you pass the trained network to that, it will, because of all the blue colors in it, and because it collectively sees all the skies, it can tell you, no, this is not a building, this is actually in the sky. So it can help a lot. So yes, there are some drifting, but the amount of drift is very, very minimal compared to the amount of new information that you're collectively reaching from the data set.
So was the label a noun name on an image file? Was it a rectangle? Was it a mask, like a mask or CNN?
So no, those labels are simply a probability vectors. There is nothing like annotated to them.
Okay, so nothing annotated.
Nothing
specific
annotated.
Region in the image.
Exactly. So basically, after the first round of the training, you completely threw away the ground truth labels, and then you just use the previous networks as a label.
I see. Okay, thank you.
Hi, thanks for the presentation. When you train on floating point, you also have some discretization there. If you could mention anything, because you mentioned that it typically facilitates the fact that you have continuous values to train, but in fact, those floating points are also discrete. Because of the precision. You have a representation of 32-bit or whatever floating point.
Oh, I see. That level of precision, that level of discretization is negligible in the back because we can capture the gradient with that level of precision. So when actually up to 8-bit, it's easy to follow the standard path of gradient descent because you can capture the value of the gradient. We are not like heavily discretized, but when you get to the binary, then the gradients are not well defined. We have to define gradient ourselves, which makes it more difficult, and that's why we need to change the stochastic gradient algorithm.
Thanks.
Okay, other questions? So let's thank our speaker again. Thank you.